Okay, so in this question, we're given that a tennis ball sits on top of a basketball such that the masses differ by a lot, right? So the mass of the basketball is much larger than the mass of the tennis ball. And the balls are released from rest such that when the balls hit the ground, basically they're stacked up like that, right? And it'll be such that the basically the basketball is going to transfer a lot of momentum to the tennis ball, and we're asked to find how high the tennis ball bounces after hitting the ground. Okay, so you can decompose this motion into a couple of parts, right? So the first part is that when the ball falls down from a height, okay, so the first segment of time is when the ball falls down from the height h, right? Oh, sorry, the height h, yeah, height h, which is, did they mention? Oh yes, here, height h. When the ball falls down from a height h, right, such that h, so it falls down, and then the the second the second thing that happens is that even though they technically hit at the same time because they're stacked on top of one another, we can actually think of it as the basketball hitting the ground first. Right? So the basketball hits the ground, and then its velocity changes. Okay, so the basketball bounces on the ground first, and then in the next moment, so the tennis ball, even though it's touching the basketball, but you can think of it as floating slightly above the basketball, so that the basketball actually does the bounce first. And then after that, the basketball um transfers. So the two objects are now going towards one another, right? And so now the the basketball transfers momentum to there's an elastic collision that happens, and after that, right, the basketball will be like this, and then the tennis ball would move up at a much higher velocity. Okay, so the main essence is this part over here. Okay, the main bulk of the work we're gonna do is in this elastic collision. The rest are relatively simple. Okay, so first stage, the two objects fall down from a height h, right? So by kinetic energy considerations or by kinematics, you know that the velocity, right, that they reach at is going to be that they come down at the same velocity. The common velocity is going to be square root 2gh. Okay. Okay. So now the second, the third thing that happens is when in the third scene, the basketball is initially coming down with velocity v, and after it bounces, um, because this collision is elastic and because the ground doesn't move, right? So we can think of the ground as an infinitely massive object, right? So the 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 momentum, right, of the basketball technically is transferred to the ground, right? But because the ground is a infinitely massive object, right, it doesn't it gains zero velocity. So the only thing that happens in this case is that the velocity of the basketball gets flipped, right? And the reason it must get flipped, and the reason that the the final velocity of the basketball is equal in magnitude, right, is because kinetic energy is conserved, right? So yeah, so the velocity vector simply gets flipped. Okay, so now we know that in this scene, right? So in the previous scene, it's just a flip in the velocity vector. When you bounce off a wall or when you bounce off a ground, right? It's just a flip, assuming it's elastic. If it's not elastic, then the final velocity will be a bit less than the initial velocity, but more on inelastic collisions later on. Okay, so in the third, in next scenario, right, we know that the basketball has a velocity of 2gh, right, the whereas the tennis ball also has velocity 2gh. Okay, so both of them come together with the same velocity, and the we can apply the elastic collision formula, right? So through all the derivation we did just now, right, we obtain the following results. So okay, let me call tennis ball A and the basketball B. So in this case, now remember that because we're doing the collision now, we need to define a direction for positive velocity. So in this case, I'm going to define the direction as upward positive. Okay, I'm going to define upward positive. So the velocities, right? So UA is going to be, is going downwards at square root 2gh, so it's going to be minus square root 2gh, and UB is going to be square root 2gh. Mass A and mass B are simply the masses of the basketball and the tennis ball. The tennis ball and the basketball. So by applying formula, so we have two choices: whether we find the velocity of B, final velocity of B, or final velocity A. In this case, because we know we only care about how high the basketball bounces. I see the question only asks, sorry, we only care about how high the tennis ball bounces. We do not really care about how the final velocity of the basketball. So in this case, we're more concerned with VA, right? So we'll use the equation 80 instead of equation 77. If we're concerned with the basketball's velocity, final velocity, then we'll use equation 77. Okay, so VA is equals to, okay, so mass of A is just small m, right? Minus mass of B, which is big M, over small m plus big M, UA. So UA will be minus square root 2gh plus 2mb, mass of the basketball, over m plus small m plus big M. Okay, so do be careful which one is the small and big when you write it out, and you're gonna get square root 2gh over here. And if we collect the terms, we'll get m plus big M in the denominator. Square root 2gh is a common factor, and we get m3 big M minus small m. Okay, so this is where we can apply the limit which the question used. The question told us, right, big M is much bigger than small m. So whenever you see something like that, right, big M much bigger than small m, you can always rearrange it such that small m over big M is much less than 1. Okay, so using this, right, we want to express this ratio, right? We want to approximate this ratio using this approximation. So what can you do, right? You basically want to you see over here we have big M and small m independently, right? We basically want to package it such that the only term that appears is the ratio of the two. And what can you do in this case? You can simply divide the numerator and denominator by big M. So you just have 3 minus small m over big M, right, over small m over big M plus 1. Okay, so now we see that I haven't changed the value of the ratio, right? The ratio, in this case, I just divided the numerator and denominator by big M, right? That's all I did. But now the only term that appears is small m over big M, right? You see that previously we had big M, we had small m individually, but now because we know the ratio shrinks to 1, we package them together in this ratio, and now we can take the limit as it approaches 0, right? And the limit in this case, okay, so not forgetting our square root 2gh over here, then now the limit, right, approximately in the limit where m over big M is approaches 0, this is just 3 2gh, right? 3 over 1. Okay, so we now know that the final velocity of the tennis ball, right, is 3 square root 2gh. Okay, so this is, it moves up at 3, sorry, not square root 3, 3 square root 2gh. Okay, so this is the final velocity VA. And yeah, so what do we know from here? we know once again that the height that it bounces to, right? So initially, when it first bounced over here, the height above the ground is just d, right? The diameter of the basketball, which is why we see all the d's over here. And now all that's left to do is to find from this velocity how high does it bounce. Okay, so equating kinetic and potential energy, or using kinematics, right? We can get that half m3 square root 2gh, half mv squared equals to mg, I'll call it big H, right? The height that it travels before it comes to a stop. And this will give me h equals to 9h. Right? So the answer is D. So the answer in this case is D. And there's also an extension. If you consider not only two, for a bit of extra, right? For a bit of extra curiosity, there's an extension of this question where not only two balls bounce on top of each other, but many balls. And what you end up with is a recurrence relation, right? So you have that the tennis ball, after it goes upwards, right, hits another ball, which hits another ball, which hits another ball, and the top ball is going to fly super fast. Okay, and that is a question in H3 physics actually. So yeah, you can watch it in the video over here at this timestamp. Yeah, so that's all I have for this question. See you in the next one.